We will start. Thank you all for coming to our bi-weekly, is it bi-weekly? Anyway, every second week seminar at RSES. I'm happy to have you all here, and I extend my respect to the Ngunnawal elders past, present, and emerging. As you know, we meet on Ngunnawal country. Normally I say another beautiful day on Ngunnawal country. I don't think I can say that today, but it's better than it's going to be later, I think, because I've heard there's going to be rain. So thank you all for coming. We have started a little bit of a tradition that the director gives some little bits of news, positive news at the start of the seminar in order to show you that you are sort of an intricate small circle of people who will be in the know, whereas the others who do not come to the seminars will not know about this. So for once, I point you all to look at that wonderful drone video we shot of our new copper roof. Now you will all ask me, do we have to have a copper roof? And the reason is it's a heritage roof, and we had no choice other than replacing the old copper roof that went through hail damage with a new copper roof. Currently it's wonderful and shiny. Best views you have is from Jochen Brox's office and Louis Moraes' office. So I invite you all cordially to knock at their door and have a look, or to look at the video on the internet. Currently, there's a discussion going on how we can get it to be green or rather to be brown. And I'll keep you posted on what happens there. And Rodri has to spend the rest of the day standing in the corner here. Thank you. Other than that, I'll be happy to tell you that Son Pam is probably not here and traveling somewhere, I'm guessing. He's a postdoc with seismology, has been awarded the prestigious Zatman lecture. The Zatman lecture is given at each biennial study of the Earth's deep interior committee meeting of the IUGG. And is awarded to a prominent young scientist who has done outstanding work on core dynamics. So great for Son. And the other thing that I can tell you is that Ashley Barnes received the 2024 COSIMA, so Consortium for Ocean Sea Ice Modeling in Australia, Most Selfless Contributor Award this week for model development contributions for the Australian community. This is the first time this award has been received by a PhD student, and this is really great news for us. And also she's not here because there is an ocean science meeting somewhere else in Australia where they all are at. Anyway, so without much ado, I present today's seminar speaker, and I'm also the one presenting the seminar speaker today because I happen to know him a little bit longer. He's a close collaborator, I would say, on a number of levels. Steve Foley from Macquarie University, who is slowly transitioning to the ANU, but hasn't yet. So Steve, short CV, Steve has done his PhD in 1986 with Dave Green in Tasmania. There's a whole lot of people who have done their PhD with Dave Green, Greg being one of them. And of course, Dave Green was a long-term director of RSES afterwards. And his PhD was on the origin of ultrapotassic rock, some rare rock types which have gained quite unanticipated importance in later times. He changed to Germany and did a postdoc at the Max Planck Institute for Chemistry in the experimental petrology group with Gerhard Brey. And then he was assistant. He was the first foreigner to actually get an assistant professorship position at the University of Göttingen in the Earth Sciences in Germany at the time. And that was quite an intriguing thing because, of course, there was a lot of lecturing and all the lecturing had to be done in German. So Steve did all his lecturing in German. So if you want to talk in German to Steve, he can do that. He did then get a full professorship in Greifswald in 2000 and received a chair in geosciences in the University of Mainz in 2003. And he stayed there until 2013 after which he changed to Macquarie University in Australia. He did, he got a couple of prizes, if I may say that so casually. He's one of the persons who got a unique combination of prizes in Germany, national prizes in Germany, the Meyer-Leibniz Prize of the German Science Foundation, the Gerhard Hess Program of the German Science Foundation, and the Goldschmidt Award of the German Mineralogical Society. He's also, where am I? So he's also designed and led a center of excellence at the University of Mainz. It's called Geocycles. It was a very interdisciplinary one, included archaeologists and so on, that ran 2005 to 2013. He was also the chair of the German equivalent of the College of Experts. And the research, and at Macquarie was the research coordinator of this college, of the Center of Excellence CCFS at Macquarie University, and set up his experimental lab there, which is still successfully run. Now he is on the ARC College of Experts, so you all better treat him nicely because he might end up reviewing your grants. And today he's going to give a talk entitled Incipient Melts of the Mantle and the Deep Carbon Cycle. Steve.
Thank you very much for that lengthy introduction. As a small anecdote, I would make a small correction to what Dorrit said when she said I was the first foreigner to be an assistant in Germany. My boss, Matthias Rosenhauer, at the time told people that, and he was corrected. No, Stefan Hoeneß is from Austria. And it was, so they definitely see everybody, even other German speakers, as being foreigners there. What I thought I would do today, since, as Dorrit mentioned, I'm slowly transitioning to the Research School of Earth Sciences here, meaning we've sold our house and I'll be really based here from a couple of weeks' time, is to do a kind of a taster of various things which people in my research group have done. This is a very general title which pins most of those together. There are some which won't appear, but I will try and cover things very broadly. I know there are people from rather different backgrounds here, and so I don't want to deepen myself into any particular part of geochemistry or petrology, but to give a more general starter for a number of things. So this basically has to do with the deep carbon cycle. I like this. You'll know if I'm talking there, because it says so on the screen. It's about the deep carbon cycle, which is basically what goes down and what comes up. Most of the things I will have to say are about what comes up. So I'll be looking here, and that's the role of the incipient melts, which carry water and CO2. I will later on get to a few experiments about the subduction of the carbon. And of course, in the future, we've got to link those two arrows and decide what's going on much deeper in the Earth. So the things I will cover are firstly the Earth's mantle, the peridotite mantle, which we're doing not loud enough? Yeah. Okay. I'll cover the things which are noted here, particularly about other types of rocks which must be present in the Earth's mantle and how those melt. They have been neglected in the past. People have assumed that the mantle consists of peridotite, so they've done tens of thousands of experiments on that. But there are a number of other rock types which people have hardly looked at all in terms of experiments. I will then have about 2 or 3 slides on the Eastern Australian volcanics, which a couple of the students have had a look at, and apply the results of the melting of the Hydrous mantle rocks to that. And then I will get to something which is particularly interesting currently, and that is the association of carbonate-rich magmas with the edges of cratonic lithosphere, where there are steps in the thickness of lithosphere, and how that might relate also to critical metals. As I mentioned, I'll try and get around to subduction of carbonates, and as a note to me at the end, I'll have some comments on global averages, because that is a thing which I will start with, and I will continue at 2 or 3 times throughout my talk to emphasize, which is that global averages are things which people will often use in geochemistry and also planning of experiments in petrology. And yet that's not what we need to look at in future. We've done enough on the global averages. What we now need to know is what specific rock types are doing and where local differences might occur and what would happen then. A number of names down here. The first row are postdocs in the project, and the lower line are, at least at the time, were a number of PhD students. There are, of course, others in the group, but these are the ones that have contributed to what I will have to say today. This has stopped working.
Yeah.
Or it just takes time. Oh. What did you do? Yeah.
The arrow, yeah.
Yeah. That's what that's good. Yeah. That's the one I pushed. Didn't work. Never mind. The mantle is made of pyrolite. We've known this for 100 years now. This is the publication which really brought it across to people. And since then, this is where people started to do experiments on peridotite at about this time. This is the early 60s, where Ted Ringwood invented pyrolite, pyroxene olivine rock. There's the recipe there if you want to make some for yourself. 3 parts of dunite, 1 part of basalt. And it was a remarkable fit to what people later have decided is probably the average composition of the Earth's mantle. If we look a bit at the history of this, I've got here a timeline for mantle petrology, and there in the middle, here, with this little green dot there, that is approximately where people really decided that it must be peridotite in the mantle. There were, of course, some people who weren't quite convinced. I've got another one up there just before 1930, and I'll show you why in a moment. The grey area is the bit which interests me, because that's where people decided, there must be water, there must be CO2 in the mantle. What are those things doing? It's not simply a matter of dry peridotite. There must be hydrous minerals. And then we came to these two terms of mantle metasomatism and mantle heterogeneity, and we're really stuck there. People have used these two terms and been very lax about being more specific about what they mean. And this is things which we have to get further than this if we're going to make much progress in the future. Mantle heterogeneity, there was a conference on this in 1980. There's a publication in 1980 about that. But even now, you can look around the journals and people will write with mantle heterogeneity in the title of petrological and geochemical publications as if it's something new, as if it's surprising that the mantle might be heterogeneous. But they don't tell you what it really means. That's what we have to get to, the details of it. I've also mentioned pyroxenites later on. I'll be looking at hydrous ones. The first experiments on pyroxenites they cropped up about 30 years ago, but the ones on hydrous pyroxenites still remain much rarer than the ones on the dry pyroxenites. This is the publication I mentioned from 1928 from Wagner. It's not the one from Bowen. Lots of people will tell you that Bowen said that the mantle is out of peridotite. You go back to Bowen's book and have a look at what his peridotite is. It's an olivine gabbro. It has 28% of plagioclase in it. This is the one from Wagner. He really knew what we think we summarized an awful lot later, that there's a bewildering variety of peridotite xenoliths, the commonest amongst them are lertzolite and harzbergite. We don't have that many pyroxenites there. There are eclogites as well, and that there are 2 types of eclogites, and even 50 years later, people were kind of refining the same sort of stuff. Very good publication from Wagner, 1928. So this is how peridotite works, and this is what most summaries in textbooks will tell you about how the mantle works. We have a pressure temperature diagram there, which has various possible thermal gradients on it. Material moves upwards. If you follow just the 1300 degree one there, here, that's what people would normally say is the temperature of that when it reaches the surface. It hits the solidus, the red line, begins to melt, and depending on the depth at which melting starts, we'll get mid-ocean ridge basalts or we'll get ocean island basalts in those 2 windows there. Everything's explained by all of that, but it's really only the major elements which are explained. We've known for a long time, and note that the first of these, and lots of this stuff in the diagram, which I've said is 2014, is really from the 1980s. Isotopes and trace elements don't fit that model. We know we have to have something else apart from just spinel peridotite or garnet peridotite, and so we need to make the mantle more complex and also look at the other bits as well as the peridotite. So we generally have this simple mantle model where that orange bit down there in the asthenosphere is just peridotite, whereas if we go up into the crust and look at lower crust, we can get there in field trips, and so we go and we expect to find this sort of thing. Really complex mixtures of rocks. In fact, there are lots of people that would say these are really the mid-crust, not the lower crust. Why is it that we are prepared to accept that this is a very complicated lower crust, but as soon as we step over into the mantle, everything just becomes peridotite and we can make a simple model of it. We can also go into the field and find other things for the mantle. Here are a few examples from 2 continents here. And we find quite a lot of donites and pyroxenites. It's not all just lertzolite peridotite. And people have begun now to make the point that we're going to have to melt the pyroxenites as well as the peridotites and decide how the reaction between those is going to happen. Another point which I mentioned at the start was that of global averages. There's another problem in discussing what migrating melts do in the mantle when they come up to the lithosphere, and that is the very definition of a lithosphere-asthenosphere boundary. Here again, 2 diagrams simply from textbooks. The one on the left is that which is used by lots, particularly geochemists and petrologists, to say they'll discuss if something comes from the asthenosphere or from the lithosphere, as if there's a line in between them, similar to the one I just mentioned between the crust and the mantle. In fact, the right-hand diagram is more realistic. We have a transition zone between what is the convecting asthenosphere and what is our lithosphere, which will stay put for billions of years. And that is the area where all the action is, where we've got to decide what's going on, where we can make new kinds of rocks. So basically on this is a more realistic diagram, although I would say that the yellow line here is not yet thick enough. It's this yellow line and the mottled bit above it in the lithosphere, which is where lots of other stuff gets stuck. And the question then is, what stuff is that? And what's going to happen when it remelts? So in terms of several stages, I like to think of it like this. We do have our peridotite mantle down there in green. We have our lithosphere, which is shown in blue, but there's an awful lot of, or there's several episodes of magmatic action which changes this. And on the right-hand side, you can see there's a kind of a telescoping of interesting stuff up towards. This is intended really for enrichment of metals here. We begin with the peridotite. We have initial melting of a peridotite, which I'll refer to as stage 1 melting. This will form other kinds of ultramafic rocks in the mantle, and we have to look at those. So this is the area in the red box, which I'll be looking at, the first stage melting and the second stage melting, and concentrating on the second stage melting because that's what people haven't done much of. Looking at the top, if we consider the critical metals, which are very much coming into fashion now, then we have lots of ore deposit geologists who will look at the surface and say, oh, how interesting this is. We've got an awful lot of, for example, nickel in this area here. But where the future is in between them, the lower crust. That's what people have neglected at the moment. There's a lot more done in the mantle in experiments than there is in the lower crust. And people are wandering around on the surface saying, ah, wonderful, an ore deposit, but they're not considering what's happening down below. So let's have a look at these things kind of in a forward modeling way. This one I stole from Al Hoffman when we were, when back in my Mainz days, we had an interdisciplinary series of lectures on all kinds of things in Earth system science. So this is Al's diagram where we're looking at the concentration of elements in the crust relative to the depleted mantle. That's the blue line. What gets stuck in the crust is on the orange line. And the mid-ocean rich basalts are these purple things here. So this is just a matter of, let's melt the peridotite partially, which elements go into the crust, which ones don't. But that's not the reason I'm showing it. I only want to look at the volatile components. Water is about as incompatible as lanthanum. People often use lanthanum as a proxy for water in ultramafic rocks, simply because it's easier to measure lanthanum than it is to water. The same thing for, oh no, first of all, another point, which is that potassium is about the same. And so if we do start with a four-phase peridotite and we melt that, the melt is going to take water and potassium at about the same concentrations. And that's the reason we will very easily form a mica when that re-solidifies. So we're going to get mica-bearing rocks. If we look at CO2, it's about the same as potassium there, a very incompatible component. And what that means is that as soon as we make a melt, we are concentrating the water and the CO2 in that melt, and we will move it around. And what I'll show you later is that the amount of melt which initially forms at a very much lower temperature than if you would melt a peridotite without those volatile components. And that means we have several hundred degrees of temperature variation where we can move these small amounts of these incipient melts around and redistribute things through the mantle. Another point there in the gray one is that if we don't have CO2, but if it's reduced carbon, this is probably a lot less incompatible, and we don't know exactly where. People ignore reduced carbon and what happens to it. It can also easily form graphite or diamond, and then it just becomes immobile again. So if we want to explain some of the very alkaline rock types, then the diagram on the left is showing you that if you were to melt a peridotite, then you cannot get that much potassium in the melt, the partial melt of the peridotite. The orange and yellow ones at the top, lamproites, shoshonites, which are extremely alkaline kinds of magmas, you simply can't get straight from a peridotite. There has to be this intermediate phase of some other kinds of rocks. The right-hand diagram is one of 20 or 30 I could have taken. That was from a previous student, Dejan Prelevich. And what that's showing you is that the amount of variation in strontium and neodymium isotopes not only shows that we have very different rocks down there, but that they've been there for a long time. So people will often say we need at least 2 billion years of enrichment in the lithosphere to explain the evolution of the isotopes. So that's the geochemistry of it. We need something else in the mantle apart from peridotite. So what do we need? People have attempted to say which minerals other than peridotites must be down there. And here are just 4 examples, again, chosen from 3 different continents. And I've colored the minerals which people are suggesting might be in the source. And here we see clinopyroxene, phlogopite, amphibole, titanium oxides, phosphate, which really means apatite, perhaps also pyroxene as well. And mica and clinopyroxene keep recurring in these suggestions here. That's what people think that we need in order to explain it. So mica clinopyroxenite is something which I'm going to jump on because I'm going to show that experiments will also show you unwittingly that mica and clinopyroxene are going to be very important when you solidify melts within the mantle. So I mentioned before that mantle metasomatism is a term that's been with us for more than 50 years now, and yet this is our clear view of what it really means. We know immediately in front of our noses what we think we mean, but if we go into the detail, it can get very foggy very quickly. I particularly like this diagram because it shows a road going straight ahead, but does that road go around the corner? We don't know if that line of trees is beside the road or if it's basically down a rabbit hole. If there's another road there and this road goes straight on, it's easy to get stuck in rabbit holes here. We have to get more information and try and clear the fog a bit to decide what the mantle metasomatism is doing. So let's have a look at it. Which mantle rocks have we got? If we look at xenoliths, then we'll find a lot of clinopyroxene and mica here. The two on the right-hand side are micro XRF maps showing you again phlogopite in red, clinopyroxene in green, but that's not the whole story. We also have different iron titanium oxides in blue, and we have apatite there in some cases as well. That's in the sort of garish green here. But phlogopite and clinopyroxene are very common here. Chu-Tian has done these maps. He's the one I mentioned on my list of people. You'll see them appearing one after the other as I go through here. What if we take some experiments? These are interesting results because they weren't intended to show this. People did what we called liquidus experiments back in the 1980s and 90s. So you would take an alkaline rock and you would want to find out what was on its liquidus, which could show you what might be in the source. But what if it gets stuck? If this melt stops and gets stuck in the mantle and solidifies there, then it's the lower temperature side of these diagrams which becomes interesting. And there you see brown, which is phlogopite, dark green is clinopyroxene, cropping up often together with iron titanium oxides. And at higher pressures, there's one from Roger Mitchell here, you see the same thing. Clinopyroxene and phlogopite, with this, in this case, with rutile as well, and apatite. Another kind of experiment, which has come across along much later, and here's a face you know. He did some experiments, Michael did some experiments with two rocks in the same experiment. He was looking at a sediment next to a peridotite. So the peridotite is the black stuff at the top in the aluminium and potassium diagrams. The sediment begins down there. That's the red stuff in the aluminium diagram, so over here. And the blue and green bit in the aluminium diagram is the reaction zone between these. And here again, the green is phlogopite, the blue is clinopyroxene. We keep making mica and clinopyroxene, in this case, not simply by solidifying a melt in the mantle, but in this case, by reacting the melt from a sediment together with the peridotite. And you'll notice in the potassium diagram, that very clearly shows you these teeth of phlogopite, that's now concentrating all the phlogopite there was in that system. It's taken it out of the sediment and put it straight into the reaction zone. I like these timelines because you can understand to some extent why people were doing what they were. Note in the middle here, have I got a, yes, I have, a box around these, where people started doing experiments on peridotite with water, with CO2, and these liquidus experiments, which I mentioned. It's only just become possible. Note just above that, piston cylinder experiments were only possible from the 1960s. And so we weren't doing experiments before that because we couldn't do the experiments before that. But as soon as we could, and we knew that peridotite was the likely mantle, it became possible to do the experiments, so people did a lot of them, and they were happy with that. They kept doing kinds of experiments. On the liquidus experiments, they died out in around 1990s because people didn't find what they were looking for. What they were looking for was the conditions in which they could explain an alkaline rock with water and or CO2 as coming from peridotite. So they would need to find the peridotite minerals at the liquidus of those experiments, and they couldn't in many cases. And the obvious solution is that they don't come from just peridotite. There's more to it than that. So what do we get if we look at some of these experiments? And here we have the first stage melting. I've only got 2 or 3 slides on this one. First stage melting, which means we're putting water and CO2 in peridotite and melting it. That's not done very often. People tend to use water or CO2, but realistically, you would have both. A student who was, you'll notice the change of logo at the top right there, because Jeanette, some of you will remember, was here doing a PhD on Macquarie money, but here in the lab. That's before we could really set things up in Macquarie. And she did experiments with both water and CO2. And the diagram on the right shows you the composition of the melts that she found. Where we have a melt which is red, it's a very carbonate-rich melt. Where it's blue, it's what you would generally call a basaltic melt. So it's a silicate melt with lower contents of alkalis. And at high pressures, 4 and 5 gigapascals, which is depths of 120 to 160 kilometers approximately, you've got this green zone. And those are carbonated silicate melts, which I'm calling over here on the left-hand side, ultramafic lamprifier. That's the kind of rock we get at the surface, which is most similar to these melts. And they don't exist when we get to higher levels, around 2 and 3 gigapascals. So they're only present down here in the, well, you could say the lower lithosphere or the upper asthenosphere. But that's important to know because these are the melts which are going to be moving around in the mantle and will transport metals. Notice also that if we didn't have any volatiles, then melting would begin over here. We have several hundred degrees drop in the melting temperature because we have water and CO2. And that again means we have this temperature area where we can, that's what I've noted over here in the upper left as the temperature range for mantle metasomatism. There's only a small amount of melt, but it's very mobile and it's going to exist over a large temperature range where you can't melt a dry peridotite. If we go to higher pressures, this bottom one is for about 5 gigapascals, then it's not quite such a flat line where we only have 5% or less of melt. We can get a bit more melt out of here, 10 to 20% melt. That's this UML, this ultramafic lamprifier, which are their melts which contain 20-odd% of silica, a melt that you can't get at lower pressures. So these are the things which we need to know what's going to happen if these melts move around, what happens if they solidify, what happens if they react with peridotite somewhere else. So let's go to the second stage melting. So this is where we are on my previous diagram. We've done the melting with peridotite. Now we're looking at the ultramafic rocks, which are generally hydrous. Now, which hydrous mineral you get in these ultramafic rocks depends a bit on the pressure. If you're at around, well, up to about 100 kilometers depth, you can get a calcic amphibole. That isn't stable anymore if you go to a depth of 120 kilometers, and there you get lots of phlogopite, and you might get an alkali amphibole as well, which is a potassic richterite, a very calcium and aluminium poor amphibole. And this is, you will see, is where we get our phlogopite and clinopyroxene rocks. So if these things form veins or dykes, then there's a bunch of things we need to know. This is the diagram which you might have seen was circulated with my abstract for today. We have here a peridotite split by a dyke, and the dyke is showing you there's different minerals in the dyke. The point I was making earlier is loads of people have done experiments on the peridotite, but very few on the mineralogy of these dykes. So which ones do we need to look at? These dykes are going to have a much more varied mineralogy than a peridotite has. And so we need actually more experiments on those, but we have far fewer. What are the melting temperatures? What's the composition of the melt which gets produced? Because is that melt just going to stay in the dyke and wander up it? Or is it going to get drawn into the peridotite and react with it? That's where these reaction experiments come in. We need to know all of that. Which minerals will react out of the wall rock. So we've been doing this for a while now. We started with compositions which were reminiscent of things we found in cratonic areas. And these diagrams are showing you the modal mineralogy against the temperature. So we started with a third each of phlogopite, clinopyroxene, potassic richterite as Kr, that's the alkali amphibole. We heat this up as we move to the right, and you see melt appearing, and olivine appears at the same time. The potassic richterite disappears very quickly, within about 50 degrees of the melting temperature, and we produce olivine as a peritectic phase. Now, what that is telling you is you quickly produce lots of melt. If this melt runs into the peridotite, it's not going to react with the olivine because it's producing olivine itself. So we need to know the melting reactions as well to really know what's going on. We have also tried 5% of ilmenite or rutile or apatite, and we get the diagrams down below, and they're fairly similar. We rapidly melt the amphibole out. We produce olivine. In most cases, in the right-hand one with apatite, we're not producing olivine because we're producing clinopyroxene. So that was our beginning. The starting point was the alkali amphibole-bearing cratonic rocks, but we also need a variety of other ones. This is now a modern summary we have of 5 publications there. And what this diagram is showing you is the melting temperature. And these little boxes show you, for one composition, which is at the top, there's the mineralogy of these things. That's calcic amphibole and apatite. The melting temperature is where the red line is. We did an experiment where the red box is and it had melt, where the black box is, it didn't have melt. And these are being compared to the melting point of a dry peridotite, that's the green line up here, or a wet peridotite, which is the brown line. And in all cases, up to now, these hydrous pyroxenites or hydrous mantle rocks will melt at a lower temperature than peridotite, even wet peridotite. So that means that if these dykes do exist down in the mantle, they're always going to melt first. And we're going to get a reaction between the melt of them and the peridotite. Not only that, it's not only a matter of the melting temperature, but the melting rates. Here we are looking at, let's look at the left-hand diagram with the calcic amphibole assemblages. And here I'm showing you the percent of melt produced as a function of the temperature. And what you see is that within 50 degrees of the initial or the beginning of melting, we have 50% of melt. That's because the amphibole melts so quickly. That's compared to the green line. The green line is showing you what peridotite does. It melts much more slowly, and it doesn't begin to melt until we have the dyke more than half molten. So these melts are going to be the stuff which is moving the critical metals. The right-hand one is for mica clinopyroxenites, which is a bit more complicated because the mineralogy of those experiments was a bit more complicated. So I'll not go into that. Let's look now at the melt compositions. Here in just one diagram of silica against the potassium-sodium ratio, these are the compositions of melts in experiments, which I've put little borders around, showing you what you get out of a dyke which has an alkali amphibole, what you get out of a mica pyroxenite, so that's just mica and clinopyroxene, and what you would get if you had a calcic amphibole instead of an alkali amphibole. And you see there, the calcic amphibole produce something like a millilitite. It's a fairly uniform bunch of experimental melt compositions. The reason it's so similar to millilitite is a millilitite has a similar composition to an amphibole. And then we're basically melting amphiboles there. The richterites will give you something similar to a lamproite. And so these are all the lamproites, the natural lamproites are the small green and red circles there. So we get distinct potassic melts and sodic melts is what that means. We get potassic melts here, and from the mica pyroxenites, we get more sodic ones from the calcic amphiboles. I mentioned I would have a short look at Eastern Australia. And so that was the work of 2 students, Josh Shea, who has moved on to Cambridge, and Anthony Lanati, who has moved on to Münster in Germany, but he's still got to write his stuff up. And the point here is that the Eastern Australian volcanics are basically of 2 types. There's a sodic series and a potassic series, just like I mentioned from the experiments there. There's not very many of the potassic ones. They are only here in this area here, and they are on thicker lithosphere. Whereas the black stuff all around the edges of Australia is the sodic series, much more common, and those are basanites to the salts then. So how do we explain the difference? First, what is the difference? This is what Josh put together. He looked at all of the compositions that were known. Some of them he measured, others are drawn from all the literature. And the purple ones are the sodic series, the green ones are the potassic series, the blue ones he filtered out as being fractionated. You don't see much of a difference in this left-hand diagram where the alkalis are put together, but if you take the potassium and sodium apart in the right-hand diagram, you see a distinction. The potassic ones have very high potassium oxide and relatively low sodium, whereas the sodic ones, the more abundant ones, are the other way on. So there's a distinction, which must be a distinction in the source mineralogy. And we now have what we think is the solution to that, and that came from experiments which were done also in our lab by Chuqian Xu, who didn't intend to solve this problem, but he was looking at the melting of mica websterite. So we're looking at OPX, CPX, and mica there, and this is his solution for it. We can discuss that this is all along the alleged hotspot track or plume track here. If we initially melt something where it's hotter, then that melt will move up and solidify again. And when it does solidify, we're likely to get something like a phlogopite websterite. And what Chuqian is showing you here is that the phlogopite websterite partial melts, that's the second stage melt, are giving you something very similar to what Josh had said is in those potassic things. So that would make perfect sense. I mentioned that we have phlogopite and clinopyroxene when it's high pressure, calcic amphibole when it's low pressure. The high pressure ones are going to give you from the phlogopite the high potassium, whereas the shallower level calcic amphibole melts will give you the sodic series. So that's what we think this difference is. Let's go now to the craton edge. I had this diagram which was based on East Africa, where we see that we get lots of carbonatites and carbonate-rich alkaline melts close to the edge of the Tanzanian craton in Africa, and I kind of generalize this to produce the diagram on the right here, which would say we could get our melilitites and nephelinites at the edges of rifts or where the lithosphere is generally thicker. If it were thin, we would get basalts like in the middle of the rift. If we are going to get very carbonate-rich melts, we may have to go back to the experiments like those from Jeanette, which are saying 150 to 200 kilometers, and we're melting peridotite with CO2. So, linked to ANU work, this is Mark's map of the relationship of sediment-hosted metals to craton edges. That's the Nature Geoscience paper from 4 years ago now. Has found a lot of traction, and one of our group, ISRA, with whom Mark is now planning to work, I believe, has done some trace element work on the experiments on the melting of these hydrous pyroxenites. Now, what you would normally think, the old story about where you get nickel and other metals, transition metals, into melts has to do with peridotite, of course, because we know the mantle is peridotite. And olivine is the solution. The partition coefficient for nickel between olivine and liquid is about 10. So all of the nickel is going to be in the olivine. So if you want to solve how nickel gets into ore deposits, you have to melt. You have to explain it in terms of olivine in the peridotite. Now, the story we have from the experiments on hydrous minerals is that in this brown box, the partition coefficients for amphiboles, be they alkali or calcic, and phlogopite are as high or higher than the partition coefficient for olivine and liquid, which means that nickel's going to get stuck in these minerals if we have them. And if we remelt them in the way I just showed you, then a calcic amphibole is going to contribute lots of material to the melt, and it's going to contribute lots of these metals to the melt. That's if we're looking at the hydrous ones. But ISRA has also done experiments of our own on carbonate melts, moving through peridotite and pyroxenite. And she, unlike me, goes into all sorts of elaborate analytical methods, such as transmission electron microscopy, which is what she did here. And what we are looking at here is a very small scale section through two sulfide crystals, sulfide blobs, let's call them. Those are the ones at the top right here. And these, the sulfur you see in yellow, calcium you see in green, these have a small film of carbonate melt around them. Now, these were cut out of an experiment at which the sulfide globules were at the rim where, or at the edge of a migrating melt. So this is as far as the melt had got. Then we ended the experiment, and so these sulfides quenched out of the melt. The interpretation is that the sulfur and the calcium were, of course, the calcium was in a carbonate melt, but it was also carrying the sulfur, and as we'll show, was also taking lots of the metals with it, the transition metals, on the way, and they were moving in the carbonate melt. If we look at the olivines, which they moved through, those are, now these are trace element analyses with laser ICP-MS. The olivines are the red dots, the dark red dots, and what they leave behind is a clinopyroxene, which are the blue dots. And you'll notice that in terms of iron, copper, cobalt, those elements are gone out of the clinopyroxenes. They've gone with the melt, the carbonate melt, which is now being found around these sulfide globules. And the two lower diagrams are showing you two of the platinum group elements, platinum and rhodium, which are also concentrated around these carbonate melt and sulfide zones. So the PGEs are moving as well. It's all very difficult to do these experiments. And so we came back to the ANU and we came to the PIFM lab, the photo-induced force microscope, where Michael worked with ISRA on having a look how, in what way these elements and the sulfur is actually being moved. And what you see here in the red is the infrared spectra, that's the spectra down here, that the sulfur is moving as sulfate. On this kind of a scale, you can see what's really quenched out of the melt, which is not easy to do in experiments. And here she's showing, or the method is showing, that the sulfur was moving in the melt as sulfate, and at the end of the experiment, when we quenched that, it's got dropped out as a sulfide. So we've got a redox quench process there. So it's carbonate melts which are moving these metals. Let's go back to Jeanette's experiments. This is another bunch of experiments which she did, in which she knew that you could get these carbonate melts or carbonated silicate melts at very high pressures from the mantle. So what would happen if these reacted with the base of the craton where we have very reduced peridotites? So that's what these experiments are showing. If we have a look, there's the carbonate melts are on the left side, the carbonated silicate melts are on the right side. Here, we start with the melt on the left-hand side. It migrates through and gets stuck here. That's simply because it got used up in the time of the experiment. And it's forming, amongst other things, lots of clinopyroxene, phlogopite in purple, and potassic richterite in blue. So it's forming, again, the kind of things which we find in xenoliths. It's leaving behind a pretty barren-looking zone of olivines, but they do have carbon dumped in them because this is a reduced condition experiment. So now we have that's published, 2022. We now have Chun Fei, who's working on this, and he has a manuscript which is at the moment in review in Nature. And his explanation of this is that those two diagrams are essentially two stages. We start with a carbonated silicate melt. We don't have conditions at which carbonate melt would normally be produced in the mantle because it's too hot for those. This will move through so that the diagram on the right here is more relevant. It reacts to form silicate minerals, and so the melt which continues to migrate becomes a carbonatite. And the carbonatite, this melt is also carrying the sulfur and the metals, as I showed from Isra's experiments. And so it's moving up towards the edge of the craton as it thins towards the craton edge, and it gets dumped there because a carbonate melt can't carry as much sulfur as a carbonated silicate melt can, and therefore it must let it go. And so we get a sulfide enriched zone towards the edge of the craton. And this diagram at the right-hand side is showing you that this is indeed true, that xenoliths, the most sulfur-rich xenoliths, sulfide-rich xenoliths in continental roots, come from those high pressures. So it's the bottom of the lithosphere, which is concentrating the sulfide and by association also the metals. So we're expecting the metals to be there towards the edge of the cratons, and that goes back to what Mark had in his correlation with the craton edges for sedimentary sulfides. So that's enough about incremental melting of going up on the right-hand side here. I've not got that much time left, so I'll show you just a few things about the subduction experiments, which again go back to Chun-Fei. And all of my postdocs have now moved on. You know, Michael is here. Isra has now moved on to the University of Western Australia, and Chun-Fei has gone to Wuhan. We did want him to stay here as a DECRA at ANU, but the ARC didn't have such a good impression of him as they do in China. Never mind. Now, I mentioned at the beginning that we don't like global averages so much. We have to look at, or with a bit more grain than that. The point which was the starting point for these experiments which Chun-Fei did was that people will tend to look at an old publication by Planck and Langmuir about GLOS, global subducted sediment. And loads of, almost generations now, of experimentalists have done experiments on global subducted sediments. But most carbonates are not global subducted sediments. They're limestones and they are chalk. And those are in these stratigraphic borehole logs are the red bits. We have limestones and chalk there, and so Chun-Fei decided, okay, let's have a look at limestone. So he took himself a realistic dirty limestone and did experiments on it. So the message is, GLOS isn't subducted anywhere. We have to look what limestones do. And these were the results. And this is published 2023. And the result was that on a normal subduction geotherm, I realize that's just one line where in fact we need to consider a zone. But what the purpose of this was to compare it with hotter geotherms, which were probably relevant to earlier in Earth history. It stays in the gray zone, which means that limestone does not melt if you put it in a normal subduction zone. It will lose its fluid, and in terms of the chlorine as well, it means it will lose its chlorine in the fluid. Whereas if earlier in the Earth's history we had hotter subduction, or perhaps even in some cases now, then we will get a carbonate. The pink area shows you that you have a carbonate melt. And the experiments, not what we expected, produced also salts. So salts, sodium and potassium chlorides, were coexisting with the carbonate melt. So what that means is that if we had much higher geothermal gradients, then chlorine was going to get subducted because it was coexisting with the melt. The melt would move away, but it didn't take the salts with it. And so it makes an enormous difference to the chlorine cycle, whether we have cold or hot subduction of limestones, if we're talking about limestones there. So this makes an enormous difference. And plotting that as the amount of residual carbon or chlorine, you see that nowadays, this is against the temperature. So the background colors there are showing you modern style subduction, and we're getting hotter through purple to green. Then the chlorine, which is the blue line, gets lost in the fluid today, but it would be much more subductible earlier in Earth history. And there's an awful lot more carbon goes down as carbonate and gets into the transition zone than if we had global subducted sediment. So it's important to know it's not just an average, it's particular types of rock that we need to look at, in this case, limestones and chalks. And so This is getting very trendy as well. This is we've just done a review on this, lots of this from Chunfei, and we're often getting to these stagnated subducted slabs in the transition zone. Those are going to have carbonate in them on a modern subduction geotherm, because we can subduct the limestone and the chalk down there, and they're going to remelt. So that this is one of the unusual cases where a pressure temperature diagram from experimentalists you can actually read by going down and then across. We're going to be heating something up, which is not a normal magmatic process. Normally you are more cooling things down and decompressing them in order to produce melts. So here we're going to be remelting the carbonates, and they're going to be moving up and doing nasty things to our lithosphere. What those two little globs are showing you is that your clastic sediments are likely to rise. As long as they're thick, they should move upwards in diapirs, and that very thick sediments of carbonate sediments are going to do the same. It's only when they're mixtures that they will get deeply subducted. Good, I think I've gone on long enough, so I'll stop there. I did have a few more slides, but they were about something completely different, so I'll not show you those.
Okay, thank you, Steve. Now everybody knows everything about experiments. Everybody knows this before. Are there any questions for Steve?
Yeah, I'm happy to start. Thanks for the talk, it was really insightful. Could you, okay, so for example, if I want to focus on the lucid dykes in Australia, so I'm understanding through what you've explained that in order to generate these melts, or in order to generate the products that are seen at the surface, we need at least 2 episodes of melting. The first episode of melting at depth, which is going to generate those secondary phases that are going to have like an enrichment in certain trace elements. And in the second melt episode, is going to remobilize these concentrated trace elements in order to generate the volcanic products we see at the surface. Did I understand that correctly?
Yeah, in fact, the model which Chuchan has for that says that it's related to the same heating event, so that you would produce at the deeper level partial melts, which then solidify at a higher level, and then they become remelted as the plume moves. In other cases, away from Australia, there could be an enormous time gap between those two. But in the case of Eastern Australia, he thinks that they're related to the same heating event, which is, well, Australia's moving across it, right? It's not really moving under Australia. But yes, and that means that the second event is melting a different kind of rock. Yeah.
And now that you're on this slide with, in a way, melting and the stabilization of phase that are stagnating in the transition zone, how different would these melts be to the first kind of deep melts available in the plume scenario for the lucid dykes? So how different would these melts from the transition zone be compared to the deep response of the plume?
Well, I guess in this diagram here, it's the difference between 3 and 5, right? So that the difference is the rocks which you are melting. What we now know a bit more about is what is going to be present when we get to position 3 there. And that if we take limestones down, we expect to have lots of carbonate left. Initially, 5 to 10 years ago, I would say, there were some people saying that you would get stuff stuck in the transition zone, and yet there wasn't the basis in experiments to say why the carbonates would get down that far. Because if you have something like global subducted sediment, they melt before that. So it makes sense to look at all these different kinds of rock And I'm sure there are rocks now at position 3, which we haven't looked at yet in experiments.
Steve, in position 3, what about redox freezing when those carbonate melts? Sorry.
Don't worry. Just the guy to your left who wanted to ask a question. Never mind.
Too bad.
Yeah, position 3, where you might expect redox freezing of those carbonate rich
Right.
Yes.
I mean, that's going to be a question as well of exactly what depth that is, right? You'll notice there is no kilometer scale on there, because they're going to get stuck at different depths, and that's going to affect firstly what kind of rocks are there to melt, and then what's going to happen when they do. What we think is, when you see the brown gets kind of darker towards the bottom of the diagram, that means it's getting more reduced as well, not just that it's getting hotter. And that means the redox contrast between carbonate melts and the surrounding brown peridotite is going to be higher. And so we are going to get the action much more quickly, I would think. Yeah. I mean, that's a complicated question.
Do we are we going to let the Welshman speak, or are we going hands up for Rodri?
So I have lots of questions. So I'd just like to go back to Thomas's point. So in your response to Thomas, you said in some parts of the world, those two stages of melting may be for a significant time apart.
Yeah.
So just for my interest, is there any way of dating those two?
Well, the reason I said that, I showed a diagram much earlier. No, what's happened? I can't see now. Oh, I'm over there. I'm not over here. Here we go. The isotopes vary enormously. I showed you that diagram. Click, double click.
So is the inference from that that in Australia they don't vary massively, but in other places they do?
Well, in that we've no the point is that the melts which you could produce at the higher pressure at this is where the geophysics helps in Australia, is we know how deep the lithosphere is and it's likely to have been, because these things are only 20 million years old, right?
Yeah.
And so we know that the melting was deep, and that if you melt something at that depth, you are likely to get a melt which is going to produce you this phlogopite websterite. And the phlogopite websterite is what we need in order to get the potassic, the lucitite suite at the surface. In other places, we just have, for example, the lucite hills here in where are they? Wyoming, aren't they? They're sitting there. They're also quite young, but we've no clue what happened in when the enrichment is. They've got very negative neodymium isotopes, which means whatever did happen happened 2 billion or more years ago. So there's no way of reconstructing what the temperature or the geothermal story was at the time. All we know is that lucite hills isotope signature and the major elements and trace elements in the lucite hills, we can guess at what kind of a rock melted and how that rock, what kind of a melt would have solidified to form that, but we've no clue when or what the geodynamic environment was.
Thank you. So looking forward to you being around more, because I have lots of questions. But so the other comment you made was for the plume, the postdoc had related it to the same motion of the plume going through.
Yeah.
So I can understand how you produce the first melt. That then kind of solidifies, and you need to remobilize that. And you said it's the same effect.
Well, yeah.
How does that actually work down?
The idea, that was this guy. The idea being that this stage here, in this diagram B, you're melting at your high pressures, but you have the slope in the lithosphere. So you've got these steps in the lithosphere thickness. In that area, you can probably tell me if that map is correct or not now, or if it's been modified. But that's an area where there's lots of differences in the lithosphere. We think that we don't just have a lithosphere 100 kilometers thick or 150, but there's a patchy bit with all sorts of slopes in between them. So it would make sense for the melt which gets produced in B to wander up to where the lithosphere is thinner. And if it does that, and then Australia continues moving, then it gets, that part then gets into the hotter bit. And that's going in the right sense of the map at the top there. So you're going from where he's got, now what's he put B twice, yeah, B and C, he's moving from where the thing is very deep here, where
So
I'll
essentially the
here,
melt is
and then to
propagating
C.
ahead of the plume, and the
Yeah.
plume is remelting.
Yeah.
I have one more for that.
Any other questions, Mark?
You said right at the beginning that you think the lower crust, there's also processes going on there that's quite important. Any kind of expansion on what things might be interested there?
Yeah, well, I think I mean, we now have this, the diagram which I showed you where we know we've done lots and lots with peridotite. We've started to do things with the next stage. What happens when that gets into the crust? And that's going to have a lot to do with how can the metals move in which melts, and what's going to happen when that gets into the crust. Because we need, what we're basically missing then are reaction experiments with lower crustal rocks. People have done lots of different kinds of melts with peridotite now, but they're not doing them with lower crustal rocks. And of course, that opens the scope massively because of the range of rocks we might have in the lower crust, which is also going to be an effect of geodynamic environment. It's going, I mean, if you consider being under the Andes, we're going to have probably a very different lower crust to if we have in a stable continental area. Lots of experiments to do, nice reaction experiments to do, which people haven't done yet with lower crustal rocks.
One question from online audience.
Okay, yes. Can you read this? How are we gonna you do that? Or I can read it out. That's it. I'll read it out. So there is a see, there is Michael online. So question from Michael Annenberg, excellent talk, thank you. I have so many questions, but Zoom isn't the ideal medium for it. Why isn't he here? Michael, why aren't you here? One question though, your opinion regarding direct mantle versus immiscibility origin for crustal carbonatites. Are some of your carbonated silicate melts the progenitors for immiscibility derived carbonatites? And what would you look for in a crustal carbonatite to identify whether it is immiscibility derived or came directly from the mantle, presumably also indicative of melting depth?
Oh dear. Yeah, and a large complex of interrelated questions. We have done experiments which I haven't mentioned, which you may know about, which is also from Israel, where we took one of these ultramafic lamprifiers and attempted to see if it would unmix, because I was saying that at high pressures, 120 kilometers, we can have an ultramafic lamprifier, but it should unmix into carbonate and silicate as it comes to lower pressures, but it didn't. This was a fairly potassic ultramafic lamprifier, and what it did was it lost a fluid. And so we were losing potassium in a fluid, and this initially intermediate potassic sodic ultramafic lamprifier was splitting into a sodic carbonatite and a potassic fluid, which kind of explains why we get potassic phenites around carbonatites a lot. So that's one thing which we think would happen when you go into the crust. So the question of a crustal carbonatite then becomes difficult, because it's not necessarily the same thing as it was when it was in the mantle. If it's going to lose a fluid on the way, it's going to evolve in terms of compositions. So I don't have a simple answer for that question of how I'm going to tell a crustal from a mantle carbonatite.
Okay, any more questions? Audrey, are you happy? Well, so just before we close up, I've got a sign-up sheet here because as is tradition, we're going to take the seminar speaker out for dinner tonight. You're all welcome to join us. Not everybody will be paid for, though, but the students will be paid for. And if you would like to come along at 6 o'clock tonight with Blue Ginger in Banda Street, I think it's called, Indian restaurant. Notch, and you can grill Steve even more about whatever you would ever wanted to know about experiments.
Can we grill them about all my food?
Absolutely,
Yes.
but I will be there. So thank you all for coming. Thanks for your interest, and let's thank Steve again for his talk.
Interesting.